All right. So, um, we have a second video for you guys since we have, 3 wonderful days of not being able to meet in person. So last time we went over majority of 2.5. We also finished 2.3. Um, and I already sent an email out to you guys here yesterday, kind of how today was going to work and some updates on the due dates and everything. So if you haven't had a chance to read it over, definitely take a look. Essentially, 2.3, 2.5, and 2.2, 2.3, and 2.5 paper homeworks, okay, are all going to be due on Monday. Originally some of those were going to be due during the week, but obviously we haven't been able to meet, so can't take them yet. So hopefully you already worked on them and got them kind of worked on a little bit. But I am going to be taking those three on Monday. And then I think we also have the quiz number 2 on Monday, which is still going to be the same quiz. It's still going to be kind of a graph, finding limits of a graph, and then doing some of the 2.3 stuff. So it's pretty much like the second half of 2.2 and then stuff on 2.3. Okay. Um, you know, so just make sure you're able to find limits, K, squeeze theorem, all those different things. Um, so so last time with 2.5, we talked about what makes a function continuous and its implications of the limit. We also looked at, what if it wasn't continuous? How does that affect things? Okay, we had those 4 different cases. We have like a removable discontinuity, we have a jump, an infinite, and an essential, right? And we looked at all the different ways that works, right? So removable, the limits do meet at the same point, but that point doesn't exist. Then a jump, the limits meet at 2 different areas, which means the limit does not exist at all. The infinite one is the limit goes to infinity. So as we're getting x closer and closer to a, then the either from the left or right side, then it seems like it's going to infinity or function value. And the essential was the catch-all, right? It was we know we have an issue, right? Because we know we can't be continuous by that definition, but it doesn't really fit the removable, jump, or infinite, then we will just say it's essential, okay? Then we had an example where we kind of gave you different facts about whatever's going on. You had to make that distinction. Was it removable, jump, infinite, or essential? Now, what this is going to bring us to is another important kind of theorem here that deals with continuity. Okay, so it's going to be the intermediate value theorem. Now, the way this theorem works is it's going to take a function that is continuous, and because the function is continuous on a certain interval, what we're able to do is we can say that there's a certain answer has to exist. Okay, so we're going to take a look at that here now. So for the intermediate value theorem, which you can also be seen, we want that one, as IVT, which is the intermediate value theorem. Okay, essentially goes like this. It's gonna be a little wordy, but suppose f is continuous on, and this is a closed interval, a to b. So we know that from this point A and to this point B, f is continuous. Now, f doesn't have to be continuous everywhere, but we know it's continuous in the interval. Okay, so technically, we're only caring about this interval, not necessarily the whole function. Okay, and we also know that f of a is less than or equal to I, which is less than or equal to f of b. Actually, we don't need the equal to parts. Get rid of that. So just less than. So we suppose f is continuous on this interval a to b, and f of a is less than this value I, which is less than f of b. Okay? So we're supposing this. We call I is called an intermediate value. And what this means is from f of a to f of b, I is in the middle. Okay. Another way this works, and kind of if you think about it, right? Let's just say you are stopped at a red light, right? Not right now because it might be a little icy out there. Let's say you're stopped at a red light, and on 501 or 544 or wherever, and after a light turns green, you start driving, right? And after about a few minutes, you look down at your speed and you see you're going 50 miles an hour, right? Well, using intermediate value theorem, the idea is since you started at 0 miles per hour because you were stopped and you're going up to 50 miles per hour, at some point between that time of you going and that time you were looking at the speed, you had to at least went 20 miles per hour at some point. You can say you went 35 miles per hour at some point, or maybe even 40 miles per hour at some point, right? Because we understand when you're driving, you go from 0 miles per hour to 50, you had to hit everything in between. Okay, this is the concept of intermediate value theorem. Is we have a starting point and ending point, and the intermediate values in the middle. Okay, now the difference though is we have a function, right? And so the way this works is if we know that f is continuous on that interval a to b, and we know that f of a is less than some I value that we care about, which is less than f of b, we call this I intermediate value. We kind of have an extra statement we can make, okay? So we can say that there exists a value C that is between A and B, which essentially is just saying that A is less than C is less than B, if you like intervals, or inequalities, I should say. So there's this value that's between A and B, so C is bigger than A, but C is less than B, such that f of C gives us this intermediate value, okay? So going back to the example with the car, right? So you started at the stop sign or red light, you're 0 miles per hour. After a few minutes, right, 2 minutes, you're going 50 miles per hour. There's some point in time, C, so whether it be a minute, 30 seconds, 45 seconds, whatever, that will produce that intermediate value of, let's say, 40 miles an hour. So, in 2 minutes you're going 50, maybe in a minute and a half you're going 40. Right? So that minute and a half is between 0 and 2 minutes, okay? And that time is producing that intermediate value. Okay, that's essentially the idea. Now, why is this helpful? Okay? Well, what we do is using the intermediate value theorem, it allows us to find roots. This is one way we can do it. So if we're dealing with like really unusual equations that are kind of a pain to maybe solve for, we can use intermediate value theorem to kind of find a root without actually doing all necessarily the hard work, right? So we're going to do 2 examples of doing that, okay, of using this intermediate value theorem to kind of see if there's a root. And again, a root just means that you have an x-intercept, okay? Now, for my visual people out there, we're going to look at this intermediate value theorem kind of visually first, and then we can kind of see how it plays into the roots, okay? So let's go ahead, we'll mark up here a basic coordinate plane, nothing too crazy. So let's say we have a point here and we have a point there. This point is going to be at A, this point is going to be at B, which means this height is f of A, and this point here would be f of B. Now, what's happening here is we know that there's some value I that's between f of A and f of B, okay? So let's say it's here. So this is going to be I. So I is between these two things. And you could also reverse this too. You could also say it's greater than and greater than. Technically, I needs to meet between the two things. That's pretty much how it works. So what we're going to do is we're going to draw this like a dotted line across here. And the reason why we're doing this is the line for I. Okay? Actually, I'll do one better. Let's actually do a solid line. I don't need you to dotted lines. So this is in a different color. We can actually just go like this. Okay? Let's assume that's really straight and flat. Didn't really do a good job there, but hey, it's kind of hard to write this thing sometimes. That's my excuse. All right, so we know that if you cross this red line, or you're on this red line, you have a value or a height of I, right? And here's the thing. We know f is continuous between a and b. So if I connect these 2 points, I don't have any discontinuity. There's no jumps, there's no removables, there's no infinities. There is going to be a line or a curve that connects these 2 points where my pen cannot be lifted off the paper. Okay? So if we do this real quick, you can have something maybe like this. Okay? This is a continuous curve. Okay? And what we notice is this curve is always going to intersect this red line and produce a point here on the blue curve. Now this point is going to be at C. So essentially what happens is we have an order pair, okay, A, then F of A, or F of A. And you have this point B, F of B. And then in between these 2 points, we have the intermediate value theorem taking place, okay, where we have this order pair C, then I, okay? So this value C is going to be plugged into the function, and it will produce this intermediate value of I. And here's the thing. I could be any value between f of a and f of b. So it could be really, really close to f of a. It could be really, really close to f of b, or somewhere in the middle. Okay? And what we're doing is we're trying to see, is there a value of x that's between a and b, that if I plug that value of x in for f, we will get this intermediate value we desire. Okay, and that's kind of the idea. So let's take a look at an example where we try doing this. Okay, so for this particular example, so this would be example 1 for today. We want to use the intermediate value theorem, IVT, to determine if we have a function, in this case it's p of x equals x to the 4th minus 5x plus 3, has a root in the interval 1 to 2. Okay, so we need to use this intermediate value theorem to determine if this function has a root in this interval. Okay, so what does this really mean? Okay, so if I say has a root, so if you see has a root, what this is implying is that that I equals 0. Okay, that's what this means. So if we see has a root, it's implying that my intermediate value is 0. So what we need to test is this. So we want to see, is this true? Is p of 1 less than 0, which is less than p of 2? This is the question. Okay? We know this is a polynomial, right? So all these polynomials we've been dealing with, these are all continuous functions. So far, we're good on continuity. But the question is this true? Right? Because we can give you 2 different points, in our interval, but maybe that interval doesn't really have 0 in the middle. Okay, and we kind of need to test that. So what's going to work is we're going to do 2 things. We're going to plug in 1, get an answer. We're going to plug in 2, get an answer, and we're going to throw it back in here. So first, p of 1. It's going to be 1 to the 4th minus 5 times 1 plus 3, right? So we'll plug that in. So we get 1 minus 5 plus 3, so we get negative 1. All right, then we do p of 2. So you get 2 to the 4th minus 5 times 2, then plus 3. 2 to the 4th is 2 times 2 times 2 times 2, so it's going to be 16 minus 10, then plus 3. So if we do that, we should get 9. And so what happens is we can rewrite this, fact that we want to be true from our intermediate value theorem by replacing with these values, right? So negative 1 is going to go in here, the 9 is going to go in here, and we're going to see what it looks like. So we're going to change this to look like this instead. So negative 1 is less than 0 is less than 9. Is this true? Is this true? Answer is yes, this is true, right? 0 is less than 9, but it is also bigger than negative 1, right? So it seems like this is going to work. So since this is true, we can say that, the root exists. So we can say that, yes, the root exists. Now notice we're not trying to figure out what that root is, okay? We just know that there's some number between 1 and 2 that if I plug it into this function, my answer is 0, okay? Because if I plug in 1, I'm smaller than 0. I plug in 2, I'm bigger than 0. So there's some number between 1 and 2 that makes this true, okay? We're not really trying to find that number per se, but we're trying to figure out, does it even exist? Is there really a number that makes this work? And so we determined that, yeah, there's some number that works because, if this is true, then there has to be some number that works, right? So we can say that, there's some c, it's like f of c equals 0 for some c between 1 and 2, right? And we can say that, 1 is less than c is less than 2. So we can say this is true. Now, what is that value for c? Not sure. We don't really worry about that at this point. Okay, intermediate value theorem is just trying to state or determine if this even exists. Okay, and if it exists, we're happy. Now, let's do one more. Okay, so it's going to be a similar question. So, for example 2, we're going to use the intermediate value theorem to determine if f of x, whoops, forgot my parenthesis there, if f of x equals e dx has a root on the interval 0 to 1. So again, so has a root, right, implies that we're trying to see when this is equal to 0. So we're trying to see, is e to the x equal to 0 using some number from 0 to 1. So essentially what we're going to be doing is we're going to be going with e to the 0 is less than 0 is less than e to the first power. We want this to be true. Okay? We want to make sure 0 is between these two numbers. Now here's the thing. E to the 0 power is 1. And then e to the first power is e, which e is really equal to 2.718 and a bunch of other numbers. So the question is this true? And the answer is no, right? This doesn't really make sense. 0 is not between 1 and 2.7, so this is not true. So what does this mean then? Well, if I plug in 0 and plug in 1, and if it has to be a root between these intervals, then 0 has to be between those answers, or those values. But it's not. So we can say that e to the x does not have a root on the interval 0, 1. Okay, so you could have an answer where it doesn't work. Okay, so we use the intermediate value theorem to prove that this is not going to work, right? So there's no value for x that I can plug in that makes this true. Okay, so none of the numbers between 0 and 1 will force e to the x to be 0. Okay, we tried it, right? Because if 0, we plug that in, we got 1. We plugged 1 in, we get e. And those are bigger than 0. 0 can't be between them. So it's never going to work, right? So this is a case where it doesn't exist. Now, e to the x is continuous on the interval 0 to 1. Okay, so if we were to look at a graph, it will be continuous. But that interval does not contain the root. Okay, so sometimes the interval provided might not be the right interval. Okay, so we need to try to make sure we can build up a case to either prove it or disprove it. In this case, we disproved that this is a interval that contains a root. And that's pretty much the idea for the intermediate value theorem. Okay, it's a little limited in its use cases, but that is kind of the idea of it. You're testing intervals to see is there a desired result there. Okay, and we don't always have to use a root. Okay, we can say, hey, is e to the x equal to 5 on the interval 0 to 1, and then we can do the same thing. Okay, so actually, let's do that. That'd be interesting. We'll do it in green. So let's say we said e to the x equals 5 instead. Well, the only difference would be these will become 5s. And guess what? We had the same issue. Is 5 between 1 and e? No. So we could even say that e does not have a solution of 5 on the interval 0 to 1. Okay, so it doesn't always have to be roots, just so you know. That's the most popular question because that's the most important one you could probably ask. But, don't be thrown off if they say, instead of does it have a root, it might say does the function equal a certain number. Okay, so I wouldn't get too bad of shape if you saw that. Now, that kind of concludes 2.5. So again, 2.5 is all about continuity. So we looked at what makes a function continuous, what makes it discontinuous, and then this intermediate value theorem does use the definition of continuity to help it, define itself. So that's why we kind of talk about it here. Now, the next section 2.6, okay, so this next section 2.6 is a little interesting, okay, because what 2.6 is related to is dealing with limits with infinities. And you're probably thinking, well, we already did that, right? We already looked at, hey, if the limit of x goes to a, and I plug in all the numbers getting closer to a, it seems like it's going to infinity. And that's one thing, but we're looking at something slightly different, okay? So we're going to start with a picture, and from this picture, we're going to try to figure out what we're talking about. So again, this is going to be 2.6 material here, okay? So start with a graph. So I'm going to make a good old coordinate plane here. We're going to use red for the curve. Let's say we have this function. Not drawn the best, but hey, it'll work. Okay? The question is this. What happens with y as x goes to infinity, or we can say as x goes to negative infinity? This is the question. So if you look at this graph, right, and as x goes to infinity, what's happening? Well, we follow the curve. It looks like the curve is getting kind of, flat, right? And it kind of looks familiar. We dealt with this when it came to vertical asymptotes, right? Because the curve will just go straight up, where the curve goes straight down. Right, this is a case where the curve is kind of going straight across, either to the right or going straight across to the left. And so this brings up a idea of a horizontal asymptote. Okay, so there's a couple definitions we're going to kind of go through first. Okay, the first is going to be this idea of, hey, you know, as x goes to infinity and is getting flatter and flatter, what is it really doing? So we're going to do that first. So here's our first definition. Okay, so let's take a limit as x goes to infinity. Okay, so x is not going to a specific number, it's going on forever to the right. So it's getting bigger and bigger and bigger forever. And we can say this equals L under certain circumstances. Okay, so this is implying that f of x is arbitrarily close to L as x is getting sufficiently large. Going all the way across. All right. So what this is meaning is as x gets closer, or I should say as x gets bigger and bigger, what's happening is our curve is kind of getting closer and closer to this value of L. Okay? And we can kind of see that here. So if I switch this real quick. So we can kind of see this here when it comes to this arrow, right? So if we kind of follow this forever, if it's getting flat, it's not really changing much in height, right? And so we'll say that value is L, okay? So what you can say is essentially, if we were to label this a little bit here, this will be L. And so as it gets closer and closer to the right, it's pretty much getting closer and closer to L, okay? Now, this brings up a second definition, okay? So this is definition number 2. This is actually describing what L is. The line y equals L. This is a horizontal line going across L. Is a horizontal asymptote when, and there's two things that can happen, either the limit as x goes to infinity of f of x equals L. So as x gets sufficiently large, the function is pretty much getting arbitrarily close to L. Or we got the opposite. Maybe the limit's going to x, but in a negative direction. So the limit of x is going, instead of positive infinity, is going to a negative infinity. And that equals L as well. Okay, so these are two definitions. The first one is defining what a limit as x goes to infinity is doing. Okay, and if that was to equal L, what that really means. So our limit as x goes to infinity of f of x equals L is just meaning that f of x is getting really, really close to L as x is getting really, really big. Okay, that's kind of the simplified version. Now, if that is happening, L is a horizontal asymptote. Okay, so if we know this is true, then that value L is a horizontal asymptote. Okay? We had a similar definition for vertical asymptote, right? If we said as x was getting closer and closer to A, and that limit was going to infinity, okay, f of x was going to infinity, then we say A was a vertical asymptote. Same concept, but it's just kind of reversed. Instead of the function going to infinity, x is going to infinity. And instead of x going to a number, f of x is going to a number. Okay, so they're kind of like inverses. of each other. Now, what we're going to do real quick is we're going to kind of consider a particular equation that does have a vertical asymptote, so we can kind of illustrate what's happening here. Okay? All right, so this is going to be example 1 when it comes to 2.6 notes. So let's evaluate the function f of x of 1 over x using a table. Actually, I need the limit. Here, rewrite this. Forgot the limit part. So the limit as x goes to infinity. Instead of writing f of x, I'll just do 1 over x. It'll be easier. Okay, so let's say we evaluate the limit as x goes to infinity of 1 over x. Okay, and we want to use a table. So going back to a table for now, because we just want to illustrate what's happening here. So if I did a table, the table method was, hey, let's pick some x's and we're going to plug them in and see a pattern, right? So we could do like 1, 10, 100, 1,000. Heck, maybe we even did 10,000 because you're just an overachiever, right? Now, what's going to happen with this function as we're making x get really, really big? We plug in 1 over 1 is 1. Plug in 10, you get 0.1. Plug in 100, you get 0.01. You plug in 1,000, you get 0.001. You plug in 10,000, 0.0001. So as we keep doing multiples of 10, because those are easier to get decimals for, what's happening? Well, as x is going to infinity, right, this is going to 0. So it seems like, using this table, the limit as x is going to infinity of 1 over x is going to be equal to 0. And then we can say that the horizontal asymptote, if you really are being asked this question, is y equals 0. Okay? So these are two implications here. Now, they only want the limit, so we don't have to include the second part of the answer here, but I am illustrating what this is implying, because that's pretty important. Right, so if the limit as x goes to infinity of 1 over x equals 0, then we have a horizontal asymptote at that value. Why? Because I'm using this definition, right? Hey, I have a limit of x going to infinity of f of x and equals L. Well, hey, f of x is 1 over x for us right now, and L is 0. So 0 has to be a horizontal asymptote. Okay? Now, there are some other ways to kind of get this done. Okay? And the one thing and the one reason why we're looking at 1 over x first is because what's going to happen is 1 over x, or things very similar to it, are always going to give us this answer of 0. It's kind of a nice little shortcut. Okay? And that's going to bring us to a lovely theorem that's using this example to kind of build out a generalization of certain types of functions. Okay, so for this theorem, we say let r be greater than 0 and rational. Then there's two things. The limit as x goes to infinity of 1 over x to a power of r. So this is pretty much any power of x in the denominator. It's 1 over it. Is going to be equal to 0. And we also know that the opposite is true. The limit as x goes to negative infinity of 1 over x to the power r is equal to 0. So this is taking example 1 and applying it to any power of x. And let's think about it for a second, right? This is pretty obvious when you start to think about what this is actually doing, right? Let's say I have x squared. Well, if I have x squared, I'm taking x times x. Well, x times x is bigger than x, right? So we know this. I'm going to jot this down. X squared is typically going to be bigger than x when you're multiplying out positive numbers, right? Now, this is going to be true pretty much always. Even if you use negative numbers, it's going to be fine, right? And so what's happening is the idea is when we are dealing with, x to a power, it's getting bigger faster, right? Well, getting big gives you 0, right? So 1 over x, if we take that limit, is 0. Well, if I do x squared, it's just getting there quicker. X cubed, also getting there quicker, okay? If we're doing x to the fourth, also getting there quicker, okay? Now, what happens, though, if you go to a negative infinity, depending on your power, it can kind of get a little bit weird because it starts to oscillate. That's kind of another problem. But generally speaking, this is what we want to see, okay? If we run into any case where it's 1 over x to the fourth, 1 over x to the fifth, 1 over x to the seventh, 10th, second power, whatever, we're going to get 0, okay? Now, why is this important? Well, this allows us to actually find some different limits, okay? So we're going to go ahead and take a look at a couple different ones here. This is probably the last example we're going to do for today. So we're going to have example 2, and we're going to have 3 parts. So we want to evaluate. So we're going to be asked to evaluate here. Part A, let's say it's looking at the limit as x goes to infinity. It's actually a negative infinity. Let's fix that. So we're looking at the limit as x goes to negative infinity, and our function is 3 over x to the power 4. Okay. All right, so how does this work? So we think about it, right? Is this similar to what the theorem says? I mean, it's pretty much close, right? The only difference is that, it's 1 over x to the power of r. So what we can do is, using our limit laws, we could technically write this 3 on the outside. Okay, so this is using our limit laws again. You don't have to necessarily go through all these steps, but I'm just going to show you real quick. And the reason why we do this is if we can take that 3 on the outside, this is just our theorem, right? Because 1 over x to the r is 0. Well, 1 over x to the fourth, guess what? That limit is 0. So technically, if it's 3 times the limit, it's 3 times 0, and guess what? That's just 0. Okay, and that's using our theorem. Now, when you get used to doing these a lot, you notice that you're always going to have cases like this where if there's a number on top, that's not really doing too much. And if you already know it's going to go to 0, then you can kind of just jump from this beginning to this end without having to do the limit law. But the limit law does kind of set it up to look like the theorem. So if you care about that, that's something to look into. All right, so let's take a look at a second one. So part B, let's say we're looking at the limit as x goes to positive infinity this time. And we're looking at 2 over the square root of x. This is going to work out pretty similarly. What we're going to do first is we're going to tweak it. The square root is really just a power of 1 over 2. So it really looks like 1 over x to the r, right? So kind of like before, we're going to see how this is going to pretty much just give us 0 again, okay? So same situation, right? We can take the 2, put it out in front, make it look like this, gives us 0, 0 times 2, 0, so it's going to give us 0, right? Ones like this are pretty simple because things look pretty decent. Now, an example that's a little bit more interesting, and we're probably going to end on here, is let's say we have the limit as x goes to infinity, but instead of having a fraction like this, we have a fraction like x cubed plus 2x minus 5 divided by 3x to the third plus 7. Now, this is substantially different than what we've been dealing with parts A and B. This is going to require us to do some interesting math trickery. So right now, this is not set up too great. It does not even look like anything really similar to the theorem, right? Because the theorem only has one denominator, and there's no x's on top. This example has multiple things in the bottom, right? And multiple things on top. They don't even have x's in them, so we do kind of have this situation where it doesn't seem like we can use this theorem. Now, we can still use the theorem, but we have to get creative. And what we're going to have to do is we're going to have to divide all the terms in this whole fraction by x cubed. Okay? If we do this, it's going to give us multiple fractions that look like this theorem that we can actually try to reduce down to maybe 0 or something like that. Okay? So if we try this, okay, it should be equal to the limit as x goes to infinity. And then we're going to try to divide all these things by x cubed. So if we try dividing all these things by x cubed, it's going to look a little bit weird, so just bear with me. So it's going to be x cubed plus 2x minus 5 all over x to the third. That's the top. The bottom's going to look like this. 3x to the third plus 7 divided by x cubed. And what's going to happen is this x cubed is going to divide into all 3 pieces at the same time. And the bottom, this x cubed is going to divide into all 2 pieces at the same time. If we do this, it looks something kind of like this. We get x cubed over x cubed plus 2x over x cubed minus 5 over x cubed. Then 3x cubed over x cubed plus 7 over x cubed. And we can then try to simplify from here. This still has a limit on it. I just don't feel like writing it out 5,000 times. But essentially, here's what happens, right? X cubed over x cubed is 1. Plus x cancels one of the x's on the bottom. So it's 2 over x squared. Minus 5 over x cubed. Divided by the x cubes cancel. So it's just 3. Plus 7 over x cubed. Now, by doing this little math trickery here, what we notice is now we have a bunch of fractions that look very similar to our theorem. Right, and since we're taking the limit here, guess what these things are going to do? All these are going to turn into 0, right? So if we go ahead and do this, our limit here, so we're going to get the limit as x goes to infinity of this fraction. Let's get 1 plus 2 over x squared minus 5 over x cubed over 3 plus 7x cubed. Okay, we can take the limit of all these pieces individually. Okay, that's using one of our limit laws. But if you do that, what's going to happen is we get 1 plus 0 minus 0 over 3 plus 0. Well, that's just going to be equal to 1/3. So here's an example where we actually get 0 this time. essentially what's going to happen is every time you have equal powers on top and bottom, okay, you can do one of these techniques to eliminate all the things that don't matter and leaves you with the two pieces that do matter. So since we have x cubed on top and 3x cubed on bottom, it really leaves you with 1/3 when you try to do this method. Now, this concept does open up a little more efficient way to do problems like this, which is using what's called the dominating term method, which we'll talk about next time in person, okay, on Monday. So we'll take a look at that then. So we'll kind of stop here for now. We're pretty much halfway through 2.6, so I think we're at a good stopping point. So we'll go ahead, we'll call it here. So as a reminder, on Monday, you do have a couple paper homeworks that need to be turned in. So it's going to be 2.2, 2.3, and 2.5. Okay, I did have them changed in middle. There are in bold in the important dates, so you understand what changed. I did change the date, obviously, date for quiz 2 to be Monday as well, because we were supposed to have that today. That didn't happen. And then I also moved the date for quiz 3, just because I don't want to give you two quizzes in the same week. So that quiz 3 is supposed to be Friday next week. I went ahead and I pushed it back into the next week, the next following week, which I think is also on a Monday as well. Okay, so make sure you take a look at those changes in the dates in the important dates tab. If you have any questions while working on the paper homework or the web assigned stuff, there's some stuff due here pretty soon on there, so you definitely want to take a look at that. You just let me know, but we'll pick back up and wrap up 2.6 next time on Monday.